Okay, so we're back with our first demo on the problems of fiber optic, and we're looking at Raylene scattering. Now, I have a tank of distilled water here. You can see it kind of moving as I jiggle the tank here a little bit. I have my laser light source. You can see it kind of lighting up the side of the tank. It's shining through the tank. You can even see it probably over here on my hand on the edge. Actually, I'll do this. You can see there it is. It's on my hand. I haven't turned it off. I'm lowering it right through the tank now. It's going right through the middle of the tank, but I can't really see it. There's no real impurities in the water reflecting or scattering the laser light source, so it kind of goes through the tank without being impeded. Well, super clear fiber optic is going to do that. There's no impurities in there, so the laser light source is going to go right through it, not affected by the glass at all. Now, that's not 100% realistic on this earth. I can make the fiber optic super clear, but it can never ever be 100% perfect. But again, going back to what Keck, Maurer, and Schultz figured out at Corning Glass, how to make your fiber from a gas, they get it almost perfect with this process. They get it almost like this, where the light source goes through unaffected. But with scattering, I'm going to now take, almost seems a shame to waste the distilled water, but I'm going to take some salt now, take a tablespoon of it, and I'm going to sprinkle it in there, and as you do, you're seeing the laser light source right there. Those particles of salt in the water, those impurities, those minerals in the water now are getting the laser light source to show up. So if my glass now starts having some impurities in it, it's not made as well, I see the light. Well, that's a bad thing in this case, because as the light is hitting those salt molecules, it's scattering. It's not going where it needs to go. It's weakening. Now, it's actually, you can actually see this pretty well. Over here, I see a nice strong light beam, and over here, I don't see it so well. It has gotten weaker because it's getting scattered. As the light is hitting these molecules over here, it's getting scattered, and it's not going as far through the tank as it used to. Now, it still does get to the other side. You can see it over there on my hand on the very edge. It's still getting through, but it's not as strong, and it's a little more diffused on this end because of these salt molecules. Well, what they had found out was, again, making the fiber optic from gas. It's super clear. I get rid of most of my impurities. But they also found that if you talk multimode fiber is typically 850 nanometers. As I start moving up to single mode, it jumps up to 1310 and 1550 nanometers. Well, you see a severe lack of the 1,000 nanometer wavelength. Because, my brain goes 800, 1,000, 1,300, 1,500, kind of like progresses. But you don't see 1,000 there. And the reason you don't is they figured out that the molecular structure of glass is made up of, the structure of glass is made up of molecules, and in the molecules there is silica metallic ions in the molecular structure. Those little metallic ions act like teeny little mirrors. So what they found was, when I use a 1,000 nanometer wavelength light source, as it starts going through that glass fiber, it's just the right size of wavelength to start hitting most of those little metallic ions, hitting most of those little miniature microscopic mirrors, and the light source into the fiber starts getting reflected everywhere. It starts getting scattered everywhere. And what actually starts happening is, I'm now going to add my scattering solution. I'm going to put a couple drops of this stuff in. This is kind of like your, like I said, your coffee creamer, if you will. You see it almost looks like a smoke in there. I'm going to mix it up now. What they started finding is, when you started using, look at that beam show up nice and strong over here now. Now that I've added these this scattering solution, almost like a coffee creamer, protein, since there's so many impurities now, I'm seeing a nice, distinct, strong beam over here, and you see it distinctly peter out, that if I put my hand over here on the far end, you barely see a beam at all. You can just barely see the beam on the edge of my hand there. Let me stir it up some more. As I stir it up some more, you'll probably even see that beam get dimmer. It's nice and strong over here. On this end, you almost don't see that red dot on my hand. It's almost gone. Well, because I've added so many impurities in here, I've scattered the light source so much, I have attenuated it so much that on this end, I'll put my hand down there again, down there by my ring, that signal is barely visible at all. That light source is very barely visible. There is so much scattering going on that I have attenuated that signal so much that that light source would not really make it through the fiber anymore. Well, they found out if I use a 1,000 nanometer wavelength light source, there is so much scattering that you get almost 100% loss. So with Raylene scattering, they figured out the light source is key to miss that window miss that 1,000 nanometer window where I get almost 100% scattering, so almost 100% attenuation. So multi-mode, super clear glass, we're using 850 nanometer wavelength to avoid a lot of that. And as we go to single mode, we jump over that area where we get most of the scattering and most of the attenuation caused by scattering. We jump over that to the 1310 and 1550 nanometer wavelengths, where it starts avoiding that. So there, when they talk scattering as one of our possible sources of attenuation or limitations on fiber, that's what they're talking about. They're talking about this phenomenon right here. When I've added all these impurities in, I've scattered that light source so much, I see it super strong here, and it peters out significantly till it almost doesn't show over here. That's what they're talking about. That is one of your problems with fiber optic. So how they solve that, make our fiber high quality, and I avoid those wavelengths that cause the massive amounts of scattering that you get. Those are two big things you can do to avoid that. All right, when I come back, we'll continue on with our discussion on problems with fiber optic, or